All right, so we're talking about the increasing, decreasing intervals is where we're struggling. Is that what I'm understanding? Okay, give me one of the problems that was a struggle for you. 31. Okay, and we'll talk about that too. I bet you were. So yes, and I was going to talk about that. We were a little rushed on Friday, and I forgot to mention it. Just like we did last year, whenever we found the maxes and the mins. Yes, and we'll talk more about that today too. We'll talk about finding them. Let's look at 31, and I'll go through so that you can see exactly how I want you to do it. All right, so 31 was g of x is equal to the absolute value of x plus 2 plus the absolute value of x minus 1 minus 2. So the first thing I need to do is graph it. Oh, I've got to get my calculator loaded on here. All right, so I'm going to do absolute value of x plus 2 So if you're on your graphing calculator, remember you are going to math over to num, and then the very first one is ABS, that's absolute value. Okay? Make sure you put parentheses after that, because if you don't, it will only do the absolute value of the very first thing instead of that plus 2 also. All right, so increasing and decreasing intervals. So as I move left to right, and always go left to right, okay, just like you read a book. Here, this piece, what is that doing? Is that increasing or is that decreasing? It's decreasing, because as I move left to right, the graph is getting lower and lower and lower. And it stops decreasing right here at -2. Do you agree with that? Okay. So decreasing would be -infinity to -2. Are we okay there? Are there, go ahead. No, it's across. So it's left to right. Yeah. So that might be where you messed up or got confused.
Oh, so it can be decreasing and
Absolutely, in one graph. Absolutely.
because I thought it was supposed to like increase.
Oh no, we're looking at intervals that it is. Oh no, I did. I was just showing you how. So it'd be absolute x minus 1 and then minus 2. Did you? Did I do it right? Look on, click y equals. Did I do x plus 2 and then x minus 1? Oh, okay, it's x minus 1. I'm sorry. All right, so we stop here, yes? And then what is this piece? Constant. So constant from -2 to 1. Do you agree with that? So constant from -2 to 1. And now we just need our increasing interval, and it might have all three, and it might only have one. It might always be increasing, always be decreasing. It might have like this one, and it might have an increasing, decreasing, and a constant. So then I picked up here at 1, and forever it increases. So my increasing interval here would be from 1 to infinity. Yes, on these. I'm using Desmos, and you're not going to have Desmos on the test, so I wanted to make sure that you could tell how to do it on here. So I'm going to go math, or actually y equals, I'm sorry. Then math and over to NUM, and the very first one is absolute value. I want to make sure I know. X plus 2, and then I want to do plus math x minus 1. And yours may not do the brackets like mine does. And then minus 2. Yeah. Y'all okay there? Huh? 31. And I'm gonna review when we get to one that's got some good bottoms, peaks and valleys. I want to show you, refresh you on how to find those maxes and mins. Yeah.
I did like
Yeah, same thing. Thank you, Brad. All right, give me other questions about your homework. Okay, so give me one just to do. 26. All right, so 26 gives you the graph itself, and it does something like this. And it says that this point, ooh, no. Yeah, but it's over here actually. Okay. Since I have this, 26. That's good. All right, so each labeled point identifies a local min, max, or neither. Identify the intervals on which the function is decreasing and increasing. So as I start negative infinity, here, yes, and I go this way, am I increasing or decreasing? Decreasing. When I get to this point, is that anything of any significance? It's a relative minimum. So remember, maxes and mins, what happens there is it changes direction. It stops increasing and starts decreasing, or vice versa. So the first thing I'm going to say is that I have a decreasing interval from negative infinity to 1. 26, sorry. And then what happens? Here I am, increasing, increasing. Does that have any significance? No, because I'm still increasing, right? I'm still going up. I might not be going up at quite the same rate I was going up. I'm going up a little bit slower than what I was, but nonetheless, I'm still going up. Up, 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 up. And then here, I stop going up, yes? What is this point called? A maximum, right? A relative maximum. It's not absolute because the graph goes up forever, but this is a relative maximum. So I stop at 5. So from 1 to 5, I'm going up. So that's an increasing interval from 1 to 5. Now what? What does it do past 5? Decrease forever, right? So from 5 to infinity. So I'm going to come back and I'm going to say, okay, that's a decreasing from 5 to infinity. No, because it's not. It said identifies a max, min, or neither, and it's neither. But you don't have to identify just yet. We're going to identify today. Technically, you should be able to because we did it last year. Say that one more time. You don't have to. You didn't have to last night. You'll have to tonight, but not last night. Other questions? Are good? All right. Well, then we'll switch gears and start today. Finish this out. What do we have to do? Let's see. All right, what I would like to do is finish this in time for you to work on your assignment in class, because it seems like a lot of you started homework in class but didn't get very far and then went home and did it wrong. So I'd rather you not do it that way. At least be able to talk through with some people in your group about working through some problems. So let's finish the analysis. Domain and range clearly stumped us. That was the hardest of the analysis, and hopefully that's the hardest of any of them. All right, let's talk about boundedness. More. This board is just... What a W. More. All right. Y'all are so ugly. Thank you, Brett. All right. Tell me, do you know what it means? We talked about this briefly in Algebra 2. We didn't focus a long time on boundedness, but we did talk about it. What does it mean for a function to be bounded? It's bound up. There is a point that the graph never goes. This is terrible. I think I have so much stuff open. Yes. The camera was going and everything else. When everything's going, it really is sluggish. Yes. A point that the graph never goes above, so that would be bounded above, or never goes below. It absolutely is. Yes. What was not very good, Brad? I didn't forget them. It's called shorthand. It's notes. It's not a... What are you talking about? For example, this graph, this function, I want to know, is it bounded above, below, or neither? Because do they have to be bounded? No, they don't have to be bounded. Anything. It could be, well,
It's bounded by the point.
All right, this was, which one did I give you? 2 to the negative x. Is it bounded above, below, or neither? Look at that graph.
It never goes. Oh wait, no, it's bounded below.
It's bounded below. There's a point that it never goes below. What is that point? 0. It never crosses over 0. It's an asymptote, yeah.
So, it's above the y. You don't want to look at the x. Now we're going up and down, right?
Yes, I'm sorry, I didn't understand your question before. Yes, it's bounded. We're looking at the y value. Above and below would be y.
So it's
Okay, so you see there's an asymptote here, do we agree? There's an asymptote on the x-axis. It can never cross that asymptote, so it is bounded by that asymptote. That asymptote bounds it and keeps it from going any lower. Yeah. Because on the bottom of the graph is where it's bounded. If it doesn't go below a certain point, it's bounded below. If it doesn't go above a certain point, it's bounded above. Where is it above? The asymptote is below the graph.
It's just worded the opposite.
The graph is above the asymptote, yes. Is that why you're confused? Because the graph is above?
Yeah, it's just the wording.
Okay, but bounding, okay, so that's, if there's a lowest point, it's bounded below. If there's a highest point, it's bounded above. Does that make it easier to? Okay, it's not where the graph is, it's where it stops. So we're not saying that the graph goes up, so it goes, we're saying that it doesn't go lower than a certain point, so it's bounded below.
It's being
Bounded
stopped.
below. Look at this one. Bounded above, below, or neither? It's bounded above. There's a point it does not go above, okay? And it goes down forever, so it's bounded above. Does that make sense? Okay, what about this one? Right. It is unbounded. It is neither bounded above nor below because it goes off in both directions forever. Do we understand bounded?
Yeah, it's just all
Are you sure?
to it.
Okay.
I get it. Or is there a way to find boundedness algebraically? This seems
We're gonna look at it. For right now, we're looking. Bounded above, below, or neither?
above.
Both. I didn't know who said it, so I was trying. I knew somebody over here. It's both. Look, it never goes higher than right here, and it never goes lower than right here. So it's bounded both. It's bounded. It's just bounded. It's bounded all along. All right. There's a point that it never goes lower than. It never goes lower than the x-axis. Do you agree? Okay. There's a point it never goes above. It never goes above y. Y equals 1, right? So it's bounded from above and it's bounded from below. Everybody okay on boundedness? Tell me before I move on. I didn't expect trouble on boundedness, I won't lie, but it's okay. All right. Unacceptable. All right, let's talk about maxes and mins. This thing does not like whenever I have my camera hooked up. We have talked about this. We have talked about lots of critical points being zeros, maxes, and mins right now, right? So let's talk about how we find maxes and mins. What happens at maxes and mins? And we talked about this on Friday. Somebody said it. What changes? It changes directions. It changes from increasing to decreasing or from decreasing to increasing. Now we have two types of maxes and mins. Remember what they are? Absolute and relative. Relative is also known as, I think they use local in your book. Well, the pages that I copied you. Oh, shame. I was talking about y'all going back and looking at the stuff and y'all don't. Coach Collins said, hopefully this week. They ordered, the whole district ordered new pre-cal and calculus books, and for some reason they're delayed. So, okay, your teachers can opt out of you getting textbooks. So what are your teachers doing? Are they scanning them in like I'm doing? Okay. What's the difference in absolute and relative? Brett. I have labeled these 1, 2, and 3. Tell me what number 1 is. Relative max. Why is it not absolute? There's a higher point on the graph. It's not the highest. What is number 2? It's relative min because these arrows go down forever. How about number 3? I am sure that most of you are, or I am assuming most of you can identify relative and absolute maxes and mins. Are we okay there? I'm also going to assume that I need to go over one more time how to calculate them on your calculator, like how to find them, left bound, right bound, enter. Don't trace. Don't trace because it's not exact. Trace is not exact, so second trace is exact. 44, this is number 44 from your homework. X plus 3, x minus 1 squared. Before I graph this, what are the zeros of this function?
Negative 3 and 1.
Negative 3 and 1. It should be crossing at negative 3 and 1, right? Right, because we set it equal to 0. All right, let's graph. What do you notice? It's unbounded. Good job. Wow, Brett. If I had one, I'd give it to you. I will go. Since I get paid, then I'll go buy one of those. I should get you candy.
I mean, none of those are any practice.
Yeah, the first day of my class.
I used to, my first couple of years teaching, I would go see by this big guy.
I got more graphs here.
All right. Brett says it's unbounded. Brett is intrinsically motivated, and I don't have to extrinsically motivate him with candy because you're doing things to better yourself, to make yourself a better math person. And so you answered that question because you are motivated. Unbounded. What's the domain? We talked about the zeros. How about? Yeah, that's what I'm gonna do. So what do you see here? Max or min? A relative maximum and a relative minimum. What is this one? Relative max. All right, so to calculate that, and if you do not remember, it may help you to go step by step with me. Second trace. No. I'm going to calculate number 4, the maximum. Adam, do not hit her with a cord again. All right, number 4. Now look what it says. It says left bound. That means I want to hit the left button until I have crossed over that maximum. Okay? If it confuses you about left bound, put your cursor as close as you can to the actual maximum and then click left 2 or 3 times. Okay? And hit enter. Then it says right bound. You have to keep reading what it's telling you down here in the bottom. So go back up close to it and 2 or 3 clicks to the right of the maximum itself and hit enter, and then it says do you it says do you want me to guess, and we're going to hit enter again. And then you're going to guess and hit enter. So what it is you're doing is you're giving it some boundaries here, and you're saying between here and here, tell me what the highest point on the graph is. That's essentially what you're doing. That's what left bound, right bound means. Make sure you can get this value for this function. Okay? That means my function is increasing from negative infinity to negative 1 2/3. Do you see that? Okay. So then I'm going to start decreasing, and to figure out where, I'm going to calculate my minimum here. So again with second trace, if you're finding the max, you want to put the x and the y. If you're finding the increasing, decreasing intervals, you just want the x. All right, left bound on my minimum now, and right bound, and enter again. 1, and then if you ever see this, a lot of you always ask me, what does that mean? This means, scientific notation, it means take the decimal 12 places to the left. And if I take this 12 places to the left, What value am I at? A very small number, so I'm going to round it to 0. 0, right? So this point is 1, 0. Go look at there. That's your minimum. So that means I'm decreasing.
I got 1.000.
What'd you get here? You talking about for your y?
My y is 1.8.
We're going to all get something a little different here. As long as this is e negative, a big number, it's going to 0. Yeah, yeah. Other questions about that? Pixelation in the calculators, and it just causes, but we know that that's 1 because it has a 0 at 1. It's bouncing off. It's what we call a repeated solution because it bounces. It bounces off right there. That vertex is at 1. But we knew that because of this original equation. Other questions? Somebody had their hand up, I thought. No? Okay. What little thing? The cursor. So what you want to do is you want to, whenever you calculate, if I'm at the minimum, so see my cursor is close to the minimum now, but it's asking me for left bound. So I want to hit left until I'm on the left side of it and hit enter. And then it says right bound, so I want to make sure I go to the right until I'm past that point again and hit enter. And then it'll say, do you want me to guess? And I tell it yes. All right, everybody okay? You don't have to be a smart aleck. Okay, stop being ugly. All right, let's talk about symmetry. And then we'll talk about asymptotes. We're going to do it algebraically. You tell me whenever we finish how elementary you think it is, and then we'll see. All right, so we also talked about this in Algebra 2. I'm not sure if you remember it or not, so we're going to go over it one more time. We have even, odd, and neither. Do you guys remember this with symmetry? Some people said yes, some people said no. What does it mean? Those of you who said yes. If I have even symmetry, what does that look like? The same on both sides. It's also known as sometimes reflectional symmetry, but it's only symmetrical about what? The y-axis. This is whenever it is symmetric. We did a Desmos with this too. And it animated the graph for us and flipped it over on itself. And if it does that, that's what's known as even symmetry. Can you think of an easy function that we've talked a whole lot about that has even symmetry? That's exactly right. That quadratic parent graph, y equals x squared, is a great example of an even function. Now, that's easy enough graphically, but we're not going to be looking graphically every time. Sometimes we're going to look algebraically. So algebraically, how do we tell if a function is even? Does anybody remember this?
The inverse.
If you plug a negative in for every x, and it simplifies back to what you started with, it's an even function. Okay, so let me show you with the basic example that we just did. This is x squared. Do you agree? So if I know that f of x equals x squared, what happens if I do f of negative x? So negative, the x becomes negative, but everything else stays the same. What happens when you square a negative number? So do you agree here that f of negative x comes out to be the same thing as just f of x. That tells me algebraically it's an even function. Does that make sense? Graphically, it's an easy to see thing. Algebraically, a little bit harder. I feel like we did this in second semester, but not in first. Or I might be vice versa. Okay. Right.
We did it in like one day on.
Okay. All right, let's talk about the odd. Anybody remember what odd looks like or what odd does? I'm not going to worry about neither right now. Over here. It's what we called rotational. And remember that it on Desmos, it mapped back onto itself. It rotated around. We could rotate it 180 degrees and it still looked exactly the same. Y'all remember that? Right, it just rotated 180 degrees. Let me see if I can find that. It's right. It won't take but a second. I know. Brett gets so aggravated, but I think that it's a great. I'm showing you this graphic I forgot about. Because you're always like, ugh. It doesn't matter. That's not what I want you to see here. There you go. All right, so here's my reflectional is the same thing as even symmetry. You see how if the y-axis here divided it, it would be exactly the same. That one most students get. It's the rotational, the odd symmetry that throws everybody. So let me show you. Also called rotational symmetry. If you rotate it 180 degrees, it still looks the same. That's odd symmetry. See how the graph, if you rotate it 180 degrees? Okay, this is even, this. You don't like anything, Brett. All right. Yes or no? Y'all okay on that? Graphically. Okay, so let's talk about algebraically. All right, so let me give you an example here. That's what I'm doing right now. Ugh. This means it looks the same. How is that still? Oh, it's not. Yes, it is. It's on my computer. Okay. I thought it was coming from my camera. Never mind, y'all. All right. So let's talk about algebraically because that's the new part here for some of us. So algebraically, if I plug negative x in, the entire function is the opposite. Okay, and that's what this means. This would mean that everything changes sign. So this was the graph of x to the third. We'll even say x to the third plus 2x. If I plug a negative x in here, I get negative x to the third plus 2 times negative x. This is a 3. What happens when you cube a negative number? It stays negative, right? So this is like a negative 1 in front. Negative 1 to the third is still negative. And then I got 2 times this negative 1, so it would be minus 2x. Everything is opposite. It was all positive to start with, now it's all negative. So that means that f of negative x is equal to negative f of x, which means it is odd. Yes. Yeah. All of those are from your homework as well. All right, questions before we get to asymptotes? That's the last thing.
How big is that?
If it doesn't do either one of those, then it's neither. Yeah. Yep.
How much room do we need for asymptotes?
Before we do asymptotes, I'm going to give you a 2-minute break because that's the big part of the lesson, is the asymptotes. Okay, well, y'all take your time. We're going ahead. All right, asymptotes. We're going to talk about finding them algebraically. We've looked at them on the graph, but we haven't talked about finding them algebraically. So I'll do the easiest first, and those are the vertical asymptotes. I might would, just depending on how much room we have. I don't know, more than that. Vertical asymptotes happen when the denominator equals 0, but there's a but wait part to this definition. And that but wait part is as long as I'm going to say as long as nothing cancels and causes a hole. So let me show you exactly what I'm talking about because this is a little bit confusing. For example, if I have x plus 2 over x plus 2 times x minus 3. And this is my function. To find the vertical asymptotes, the first thing that I want to do is I want to think about situations where the bottom equals 0. But before I do that, do you notice that these two cancel out? Because these two cancel out, that means, remember we changed the sign, right? X equals negative 2 is a hole in the graph. Remember we talked about those removable discontinuities or the holes? It's called removable because I can remove it from the equation, but it still creates a hole in the graph, okay? Even though this simplifies down to 1 over x minus 3, because it was there to start with, I have to put a hole in the graph. Do you understand that? Does that make sense to you? That creates a hole. If it cancels out top and bottom, it creates a hole. Now what's left is this x minus 3, right? So where does x minus 3 equal 0? Well, that's at 3, and that means that is a vertical asymptote on my graph. So most of the time, it's not going to be a hole. 90% of the time, it's going to be a vertical asymptote. But if you get in a situation like this, that means it's a hole. There's not a vertical asymptote at negative 2. There's just a hole in the graph at negative 2. So I don't know what this graph does, but it's going. In fact, we can graph it. It's okay. It's all right. We'll come back to that later. But whatever the graph does, there's a hole at -2, but there's actually an asymptote at 3. Does that make sense? So it's undefined at 2, but it's not an asymptote. So let me show you horizontal and vertical, and then we'll do some examples of both. Yes, if we're talking about rational functions whenever we're in a fractional situation. That's when you're going to have the. And remember, if you're talking about domain, we set the bottom equal to 0 and find what it doesn't equal, and that's not in the domain. So here, -2 would not be in the domain, and 3 would not be in the domain. And 2 wouldn't be in there because it's a hole, and 3 wouldn't be in there because it's an asymptote. Because technically it cancels out with this one up top, and if they cancel, it creates a hole. Yeah, I'll graph it. Let me go into Desmos here. Tell me what I had there, because I don't x plus 2 divided by x plus 2, x minus 3. You see at 3, I have my asymptote. That's a vertical asymptote there. It looks like there's a graph at -2, but if you were to go to -2, what does it say? Undefined. And it's undefined because that's a hole. Remember I told you when we graph it by hand, we exaggerate that hole so that you know, and we make it big so you see that it's missing that point. On a graph like this, you would have to look at this and know that that's a hole there. But that's why. Does that make sense? Y'all okay? All right, let's talk about horizontal asymptotes. Again, we're talking about fractional situations, okay? And as we look at horizontal asymptotes, whenever I start talking about this, I'm going to analyze the degrees of the top and the bottom. What's a degree? The exponent, the biggest exponent, right? All right, so I'm going to set up 3 scenarios, and in all 3 scenarios, they're going to tell me where my asymptotes might be. Top heavy. So if my asymptote of the top if my degree of the top is bigger than my degree of the bottom. Are y'all following me? Top and bottom of the fraction, okay? So let's say I'm in a situation like x to the 3rd divided by 2x squared. What do you notice about this one, besides it being linear? About asymptotes. Or let's just say divided by 2. Yes, so it's top heavy. So do you notice anything about asymptotes here? It doesn't have one, right? So when I'm in a situation where the degree on top is bigger than the degree on the bottom, there's no horizontal asymptote. Y'all okay there? If I'm bottom heavy, the degree of the bottom is bigger than the degree of the top. My asymptote is always y equals 0. And if I'm in a situation where they're the same, this is whenever I have a slant asymptote or a different kind of asymptote. This, no slant, but this is going to be the leading coefficient of the top divided by the leading coefficient of the bottom. It's a ratio of those numbers. And I'm going to do several examples to show you, so I don't want you to flip out on me. But this is definitely the hardest part, I think, of the rest of the lesson, is finding these asymptotes. This is number 56. Find all horizontal and vertical asymptotes. So I have f of x equals x minus 1 over x. Let's talk about vertical first. Vertical happens when the bottom's 0, yes? But as long as nothing cancels out. So what are the vertical asymptotes here? Or does it have any? Bless you. Well, you're subtracting and not multiplying, so they don't cancel. Vertical asymptote. Does it have one? If so, what is it? 0. X equals 0. It should have a vertical asymptote at x equals 0. The bottom, where the bottom equals 0, is your vertical asymptote.
How do you know that?
I make it equal 0 because that's an undefined point. Just like I left it out of my domain, it's out of my domain because something's happening there. It's either a hole or an asymptote.
So if there's not
Fraction. Oh. No, it's the bottom equals 0. If that were 2x, then where does 2x equal 0? If that was x minus 1 over x plus 3, where does x plus 3 equal 0? So x equals negative 3 is your vertical asymptote. It just happened to be just x there.
So even if it was 2x, it'd still be 0.
Yes. Because I'm subtracting, and that would kill a kitten. Only when you multiply. Means you can't cancel out. I can't come here and just cancel these out because you can only cancel out when you're multiplying, not when you're adding or subtracting. Okay, so for the horizontal asymptote, I have to decide which scenario I'm in. Okay, am I top heavy, am I bottom heavy, or am I the same? I'm the same because the exponents here are both 1. Do you agree? Okay, so because I'm the same, I should have a horizontal asymptote at y equals, what's the leading coefficient of the top? 1. What's the leading coefficient of the bottom? 2. Oh, I added that in there. I'm sorry. I did. Well, I added it back in there. So if I graph this, I should have a horizontal asymptote at 1, and I should have a vertical asymptote at 0. So let's graph it and look and see if that's what happens. X minus 1 over x. Come on. Minus 1. Is that the situation represented by that graph? Vertical at 0, horizontal at 1. Yes. What's the domain? Negative infinity to 0, a parenthesis, and then from 0 to infinity. What's the range?
I need the vertical one again.
Exactly. Domain here we said was negative infinity to 1, to 0, and then from 0 to infinity because we left out that where the bottom 0. And the range was negative infinity to 1, 1 to infinity. Let's do one more together. Okay. All right, one more, and I'll be done. This is, by the way, number 62. I want vertical and horizontal asymptotes. And I'm going to give you a hint before y'all get too far into here. What?
Yeah, I was gonna. Do we get the same answer, or do we have to plug it in?
You'll get an extra vertical asymptote, so it'll be the same. You do. Okay, so why would I need to do it this way? Because in this situation, there you go. This is not an asymptote, this is a hole. So x equals 2 is not an asymptote, it's a hole. Okay? Not the same. It's not the same. For the vertical asymptote, though, then that leaves me with this piece. So where does x plus 2? No. No. Yes. No. A hole is not a vertical asymptote. A hole is just a plate. It's just a hole in the graph. But understand, this means that this is not in my domain and this is not in my domain. So my domain is negative infinity to negative 2, then from negative 2 to 2, and then from 2 to infinity. Just like whenever we were doing domain and we set the bottom equal to 0, and anywhere it equals 0, we leave it out of the domain. So here we would have to leave out 2 and negative 2 from my domain.
Wait, but we took out on like.
We did, but it's still a hole in the graph, and if it's a hole in the graph, it's undefined. It's not part of my domain. Yeah.
How do you know if it's a hole or the?
If it cancels out, it's a hole.
And the asymptotes are when you're on the bottom.
Yes. As long as nothing cancels. Yes. Well, you solve it. Yeah. That doesn't impact your vertical asymptote. You set the bottom equal to 0 and solve. Okay, for the horizontal asymptote, it's bottom heavy. And what does bottom heavy mean? Yeah. Okay, so I had here, it was negative 2 and positive 2, right? But because these canceled out, that's a hole and not an asymptote. So that only left this one for my asymptote. Right. Because that 2 is still a hole in the graph. If I were to graph it and go there, it would say undefined because there's not a point. So it would be like this. Other questions? Y'all want to do one more, or y'all okay?
How did you know it was bottom heavy?
Because the bottom had a degree of 2 and the top had a degree of 1.
Oh, okay. When you cancel the x minus 2.
One more. Yes. Now, horizontal asymptotes are left out of range, so negative infinity to 0 and then 0 to infinity, as long as nothing else is happening. Let's do a top heavy. We haven't done that. All right, vertical asymptotes first. Set the bottom to 0, yes. What do you notice? It's an imaginary number. Are we graphing imaginary numbers? No, so guess what that means? That's okay. I don't always have to have vertical asymptotes, huh? Imagine when I have a negative number under the square root. That's okay. How about my horizontal asymptotes? What situation am I in? Graph it and see if that makes sense. I'm going to post y'all a little reference sheet tonight on Classroom. If you want a hard copy of it, come by at the end of the day and I'll have some copy, but I'm going to post you a reference sheet on. Well, I can't do it while I'm teaching. It'll be during fourth block. I have to make it. Let's graph this one. So it was x to the third plus 2 divided by, I'll see if I can find one, Brett, before you go. No asymptotes, right? There's actually a slant asymptote here, but we won't get to that just yet. We're just looking at vertical and horizontal right now.